I will give you guys a couple of seconds or minutes, think of the solution, and I will come back. Notice that if you take the partial derivative of u with respect to y, you get partial of u, partial of y. Once you take the partial derivative of that expression with respect to x twice, you will get back to that expression that we have in the first term. And according to Clairaut's theorem, or Schwartz's theorem, the order of differentiation does not matter in continuous second-order mixed partial derivatives. Though this is of higher order partial mixed derivatives, it can still easily be derived. So after that, we substitute that to the original equation. And notice in our first two terms, we have a partial of u with respect to y. We will let p equals the partial of u with respect to y. So that will give us the second order partial of p with respect to x minus y squared p plus y cubed is equals to 0. Now, let's just group the terms with p and isolate the ones without p, which will give us this neat equation over here. Now, notice that this looks like a second-order ODE. We can solve it as a second-order ODE. So for the case 1, we have the homogeneous solution. For this one, we take the characteristic equation of it, which is r squared minus y squared is equals to 0. Which gives us r is equals to plus minus y, which will give us the homogeneous solution. Note that I made the constant terms be functions of y, because remember, we made y a constant in this equation. Now we will move on to the particular solution. For this one, we don't really have to do anything major. All we really have to do here is make the substitution p is equals to f of y, because when we do that substitution, first term here is differentiating it in terms of x, but it is a function of y. It's just gonna zero out, and once that zeroes out, we will only be left with f of y is equals to y. And now the final equation in terms of p will be, now note that we have a condition for the partial of u with respect to y. Using our equation in terms of the partial of u with respect to y, we make the substitution by matching the terms of the things here. We will notice that the e sub y has no matching term on the right-hand side. So c sub naught is just 0. On the right-hand side, e to the negative y has a coefficient of 1. c sub 1 is equals to just 1. So we get now the equation. We can verify that equation by taking its partial derivative with respect to x and then taking its limit as x approaches infinity. Now we have this expression. What do we do with this one? Well, we will integrate both sides with respect to y. It is a function of x because remember, when you partial differentiate in terms of one variable, a function that is based on a different variable in the function will get cleared out. So now, using the condition for u x0, we will get this expression, which will lead us to c sub 2 of x is equals to x minus x squared over 2. And now the final equation is presented in front of us. For the final step, we simply make the substitution x equals 1 and y equals 1, which gives us the final answer 1 minus e to the negative 1.